Hi everyone. Today I'd like to talk about one of the first questions we get asked on the chat in the website. And that's, what is Codename One? Now, my 2-second answer is obviously it's Java for mobile application developers. That's sort of the quick answer. But it kind of hides a lot of the complexity and the history. So this is really the long version of that answer, which includes everything that describes what Codename One is. Now, even if you've worked with Codename One, built an app and shipped it and did everything, I'm sure there's something within this presentation that you didn't know or didn't remember, and even I had to look up a couple of things like how many releases we've had since we launched, which is something that literally surprised me. So first let's start with a bit of history. So the origin of Codename One is when Chen, by the way, it's not Chen, it's Chen, if you only saw his name online, Chen Fishbane, started the Luit project at Sun Microsystems back in 2006, 2007. And he started it with the goal of ending device fragmentation. Back then it was the mobile device fragmentation. It was before Android existed, it was before iOS obviously existed. So device fragmentation was mostly J2ME and RIM devices back then. And he built something, it was used internally. The project for which it was built actually eventually closed down, but the library sort of became very popular. And we saw the potential, and eventually we started working with customers, and eventually we open sourced it in 2008. As part of Sun Microsystems, it was a big announcement, Java 1 main stage and everything, and a really big deal, and it gained quite a bit of community traction. The problem is it was standing on top of J2ME, which was declining fast, and some support for RIM. The community came through and actually did a port to Android, which we were prohibited from doing because of all of the complexity related to that. And we had some proof of concept ports to iOS that worked, but again, not something we could release as part of Sun Microsystems and not as part of Oracle later on. So eventually, in 2012, we left and formed Codename One, both myself and Chen. And there we took that open source project as the bit of the beginning and built the whole thing around it. The whole thing that is Codename One today is much, much bigger, and you'll see in the following slide of what it actually is. So, and since then we've gone from literally zero to millions of installs, hundreds of millions of installs, 10 releases, and added lots of additional platform support besides the iOS and Android with which we launched. We also added things we never imagined that we'll add, like JavaScript support and desktop support and Windows support. We built 3 ports for Windows. Nightmare. But it was a huge journey to get to this point from that beginning. But let's take a step back now and look at what that is. So from the list, these are essentially the 5 things that are Codename One. And it's really a combination of all of those together. So I'll talk about each one of these sentences in the next slide, in the next few slides, because for each one of them I want to talk more in depth. And the thing is that one of the reasons we came up with the name Codename One was really by accident. We literally had a code name written on slides, and sort of, yeah, it sounds nice and the URL is available, let's take that. But the thing is that it really fits. We take these 5 completely separate things that are supposedly unrelated to one another, and we ship them as a single product. You just install the IDE plugin, and that's it. Codename One is installed. And that's why, in retrospect, that's why we call it Codename One. It sort of works. And we decided that we like that. So anyway, the first thing is a virtual machine. Now, on most platforms, we don't actually ship a virtual machine. So, for instance, on Android, we just use Dalvik or Art that exists, works there rather well, and we just work with that. For the desktop port, we can just embed the JRE from Oracle into the port and essentially just ship that. But some of the platforms that we target don't have Java built in. And the best example for that is iOS, which doesn't have Java support. Initially, when we launched, we used an existing product called XMLVM, which is an open source project that translates bytecode to C code, essentially. And it worked reasonably well, but it wasn't really well maintained. It was huge. It had a lot of complexity that we didn't really need. And eventually, when we saw the project winding down and it had lots of issues that we constantly struggled with, we decided that the right thing to do was to build something of our own. And in retrospect, that was a very good decision to make, because we wanted to keep the simplicity of XMLVM and wanted to simplify it further by having the bytecode translated to C and not directly to ARM code. And this is really important, because when we translate to C, we can compile using Xcode, using the official tool that Apple ships. And that's crucial, because that means we'll be future compatible to any version of iOS that Apple ships, because they won't stop supporting C because all the games are built with it. Everything is built with it. So Codename One will always work with Apple's products with minimal changes at best. For instance, they came up with ARM64 a while back, and a lot of competitors scrambled to try and support that. And they have bitcode now, which again, people are scrambling to support and don't support. We support both without much of a problem, just flipping a switch. And the reason for that is the very conservative approach of transpiling to C code instead of directly to ARM assembly, which would be problematic. This has another advantage, that we can actually take the compiled code, essentially the C project, and with the include sources feature, we can literally run the compiled application on Apple's tools and debug and find issues. And it's easy for us when we find an issue in Codename One itself. But a lot of developers also use it to debug and profile their projects, which I'll talk about in the bootcamp as well. Windows works a bit differently. We had a version that transpiled to C#, but that was problematic because of small, really painful nuances between C# and Java that make it almost impossible to do something like that in an efficient way. So instead, we chose to adapt a port of IKVM, which is a virtual machine that takes Java bytecode and runs it on .NET. And we took that and adapted it to work with the Universal Windows Platform, and it's we got some community code and we forked it and we did a lot of work there, and it's on our repository, just like our VM JIT, which does VM that does the bytecode to C translation. All of that is open source, obviously, and it's a pretty huge project that we did just recently last year, and it's working reasonably well. And the last VM that we have essentially is one that we didn't write at all. It's TVM, and it works beautifully, and it transpiles Java bytecode to JavaScript. And it works in a very similar way to GWT, but doesn't require the source code. It works with a bytecode, and it's more efficient, more modern. It works with threads, which is really impressive, and it's a pretty great solution. So that's one of the few solutions that we're able to take as is and just use it. So it's a pretty nice solution. So that's the virtual machines that we use. The second piece of the puzzle is the API for all devices, and that's what essentially Luit evolved into. So a huge part of that is the user interface aspect, which includes a lot of the legacy of Luit. So sometimes if you see something in Codename One that doesn't make sense or looks like it's old, it's because it is old. We built on that infrastructure that took us years and years and years to build, and we kept on building on top of it, because essentially Codename One is to some degree an operating system of its own, and that takes years to build, and we've had these years to build that with a big open source community back at Sun Microsystems that also did a lot of that work. And we've got this huge API for mostly user interface, because that's the biggest piece of pretty much any mobile application. But we also abstract everything else, from file system to storage to databases to media to pretty much anything you'd expect. There's some legacy there, but that's actually part of the good, because it provides stability and continuity. The porting layer is the Codename One implementation, and that's something that allows us to separate the API that's portable to all the platforms from our specific implementation. Now that's a mostly hidden piece of Codename One. We hide it behind package protected fields and things like that. You're not supposed to touch it because it's an implementation detail and might change without warning. But essentially that's the piece that allows us to port Codename One anywhere. So for instance, the JavaScript port, the VM is open source, but the port itself is something that we actually had to sit down and write this huge port where we draw on the canvas and do all of that stuff behind the scenes to get everything to work in the browser. The same thing is true for iOS, where we spent a lot of time writing a lot of OpenGL code and all sorts of other 2D graphic code and you name it. All of that is written in native C and Objective-C to map everything to the requirements of the API. And that's how we maintain portability for all the various platforms. Now, the lightweight UI approach, I'll talk about it more in depth after I finish this segment, because it deserves its own discussion. The whole UI uses that approach, and that's probably the biggest differentiator between Codename One and pretty much everything else that is out there. Although there's quite a few, it's not a new invention that we made. It's a very old idea that originates from Smalltalk, and it's pretty much the only way to build a completely portable platform. Now, the API itself is really simple. It's designed for portability and to be really easy to use. So some things are sometimes oversimplified to keep them sensible, but it's designed to still be flexible enough so you could do anything. You can control any pixel, you can do anything. And the last thing, and this is really important, the API on the device is statically linked. Now, that dynamic linking is a very powerful tool if you're building an operating system. If you're building an app, static linking has huge benefits because it provides you the stability and consistency that you'd often want for your apps. So, for instance, if I build an app and ship it, I'd like it to be as stable as possible, and I wouldn't want something to change suddenly with a running app. But if you depend on an external library and the operating system replaces that library, your app might break because it depended on something that might be minor in theory, but could be devastating for your app. So Codename One's library is statically linked in, and one of the advantages it gives us as the developers of Codename One is that we can move fast and sometimes break things in terms of compatibility, because we know that shipping apps won't break. If your app has already shipped, changes that we make right now won't break that app because that app is oblivious to the changes that we've made to Codename One because it's statically linked. If you will try to rebuild the app, you will find that something broke. But then you will find it at that point and fix it, or notify us and we'll fix it. And that allows us to move faster than, say, Google. So for instance, Google, if they change something even minor within Android, it might break shipping apps. And that's a huge problem for them. So they need to move very carefully, and they often break things, and it's a disaster. In our case, if we break something, it isn't as big a deal for our users because you can see it and you can fix it. And there's also versioned builds that allow you to build against a stable release within Codename One. And that way, even if we do break something, you can still target a specific version and won't fail on that. So the IDE plugins are often given more credit than they're worth. The IDE plugins are relatively simple containers that contain the whole shebang. So you install them and they include the pieces of the API and project templates, and they include the tooling, which I'll talk about in the next slide. But they themselves aren't that clever. They don't include that much logic. They generally serve as a sort of glorified installer for Codename One's tools and for our templates. They don't really include that much logic within them, but they're useful as an installer essentially. Now the tools are the brains behind everything. So we've got build tools, which are essentially based on Ant, and I can go into a long discussion on why we chose Ant. Mostly it was legacy, but we've evaluated other build approaches like Maven and Gradle, and we constantly looked at options like that, and they don't provide an advantage for our very, very narrow use case, and only disadvantages. So I'll probably write about it at some point, but we don't have an advantage of leaving Ant, and it makes a lot of sense because it's very familiar and is supported by all IDEs except for Android Studio. But it works on IntelliJ, it works on Eclipse, it works on NetBeans, so that's great. And we also have the device simulator, and that's crucial. For the device simulator to work, we need lightweight architecture, which I'll talk about later. Otherwise, this would be impossible. We've got two GUI builders essentially, the new GUI builder and the older one, which is inside the resource editor / designer. The resource editor / designer serves as a sort of universal tool, sort of a Swiss Army knife that provides theming, localization, image management, and obviously the old GUI builder. And all of these tools combined are essentially the ways you interface with Codename One besides the API. And they're really important for that. And the last piece of the puzzle, and possibly one of the more controversial and important pieces, is the cloud build. Now, with recent versions, we also support offline build, but if you'd actually use that, you'd understand why we have the cloud build. Offline build is painful. You need to have a Mac if you want to build for iOS. You need to configure it in a very specific way, and this is very error prone and things can fail in lots of annoying ways. And that's just for Mac OS. If you want Windows builds, then you need a Windows machine and different type of configuration, and that's a pain in its own right. And Android also, the installation of the right versions of the SDKs and everything, it's hell on wheels to get a build setup working. So we essentially have machines in the cloud that are set up properly to build our current versions of the applications. And by the way, these are things that we need to constantly update because Apple releases a new version, Google releases something new, and so forth. So we constantly need to update these machines with additional tools, versions of the SDKs and things like that. So this is a really something that's much simpler thanks to the central management of this. The build tools essentially communicate with our cloud and essentially send tasks that are later on picked by the build server, compiled with native tooling, and that way you don't need a Mac thanks to the cloud build. And the build is actually faster. I personally use the cloud build even though I can use the offline builder because it's faster and it's easier. So when I use offline build, it's much slower. So because the machines we have in the cloud are more powerful, it's actually faster to send my jar into the cloud and get the binary back than to build everything locally. That surprised me when I first found that out, and I have a relatively powerful laptop, so it was weird. And it's a bit controversial because people sometimes have issue with sending things to the cloud, and I don't think that's as much a problem in 2017 because we use Dropbox for everything and we store important files everywhere, and it's not as if our computers are halos of impenetrable security. So the idea, our cloud is secure and we do spend a lot of time there, but source code theft existed in the 90s, and our cloud never gets your source, it only gets your bytecode. So in that sense, it's a very secure solution. And I think most people who have an issue with that haven't really gone through the various ways in which offline build can fail. And all of these ways that it can fail are applicable in the same way. Anyway, the thing I wanted to focus about most here is the lightweight architecture, because I think that's probably even more controversial than the cloud build approach, if that's possible. And that it's one of those things that is sometimes hard to convey to developers, both in terms of how it's the advantages and the disadvantages. So first, let's talk about what frameworks you might be familiar with that are lightweight versus the ones that are heavyweight that you might be familiar with. Now, notice, by the way, lightweight architecture, obviously a UI aspect, not so it's irrelevant to the other aspects of Codename One. So Codename One is lightweight, and Swing and JavaFX and Qt are all lightweight architectures. I did mention Flash and lots of other frameworks are lightweight frameworks. And heavyweight frameworks, there's several examples: SWT, AWT, Xamarin, Accelerator, all heavyweight frameworks. To one degree or another, some frameworks mix heavyweight and lightweight to some degree. Mostly, if they mix it heavily to one side, then they're considered heavyweight. If we allow some heavyweight widgets, but I digress. So the word lightweight is sometimes, when I used it to refer to Codename One, sometimes people, hey, you're making fun of other frameworks as if they're heavyweight. Well, it's not a term that we made up. It's a term that comes from Swing. And originally, it was used to differentiate between swing and AWT. Now, in a lightweight framework, the framework draws its own components. In a heavyweight framework, it uses native widgets for everything. And that sounds more efficient, but it isn't, because you need to constantly communicate with the native system, and that carries a weight. And in that sense, it's heavyweight. So that term was given by the Swing team to indicate that that it uses lightweight architecture as opposed to the peer architecture of heavyweight frameworks. Now, the best way to describe them, you can't really say that one approach is better than another. Well, I can, okay, I'll go with it. I'll go on a limb and say lightweight is better. But obviously that's an opinion. There's facts that work for both sides. Both sides have reasonable claims. I think that lightweight has better claims objectively, but obviously I'm biased, so it's hard to tell. One of the things that I've noticed over the years, well before Codename One, when people would argue between SWT and swing, this is a religious debate. You either buy into lightweight or you buy into heavyweight. If you bought into the religion, there's little that I can say that will sway you one way or another. If you are one of the swinging votes in the middle, or if you're on the lightweight side, then that can work. Otherwise, if you're so gang-ho on heavyweight, well, not much I can say. So in lightweight frameworks, we draw our own widgets. That means literally every pixel in the screen is under our control, and that's a huge advantage. So for instance, I can just overwrite paint on a painter and just draw in a specific location and be able to do very complex and yet still portable code. And we handle the events and user input for pretty much every widget. So when we draw a button, we literally draw the lines of the button or the images that represent the button, then the text, and when a user touches the screen, we detect, oh, he touched in the area of the button, and do all of the things like the button press animation and everything. We literally do all of that. We lay out the widgets, we arrange them, we do everything. That's why it took us so long to build Codename One, to build Luit essentially, and then Codename One, because we needed to do all of that, and that's essentially replicate what the operating system does. And we also provide all the tooling that's related to that, from the GUI builders and APIs and everything. Heavyweight goes the other way around. In some regards, it's simpler to implement for the guys building the framework. They just wrap the native platform. You know, I'm saying just, it's not necessarily as simple as that, but often it is, because some of the heavyweight frameworks are just scripts that take the native documentation and map it directly. The API is generally thinner and simpler because they can't go much beyond the native widgets. If they try to be portable, they need to restrict themselves to the lowest common denominator, where in lightweight frameworks I often refer to it as the highest common denominator, because we can implement things that aren't available in a platform in a way that's portable. Whereas with heavyweights, this isn't usually done, and when they do that, it's often harder because they're kind of working against the platform. And it's all of the things like the layouts and everything might flunk if you use them in a way that they're not supposed to be used. So, and one of the more important things about heavyweight is that you need to use the platform native tools. So for instance, if you're using a heavyweight framework like Xamarin, you'd need a Mac to debug an iOS app. Otherwise, it just won't work, because you'd you really need Apple's simulator to run your application. You can't run it with your own simulator because they didn't implement the functionality there. They only implemented wrappers around the functionality built by Apple. So with the lightweight framework, we can sort of hide. Apple doesn't really exist for us. We can debug on Windows an application and it will work. And with Xamarin, and this is really where we're getting to the advantages, with Xamarin or with a tool like that, you'd end up having a layer on top of the native tool, and in that case you take all of the complexities, all of the bugs, and all of the issues of the native platform and add to them the framework issues. So I've heard some people complain about some of the native frameworks, the heavyweight ones, that they're not as stable as they should be. The problem is when people make that complaint, you never really know if the problem is within the framework or within the user's installation on his machine, where he might have installed it on an unsupported version of Xcode or something like that, and something in the connection there broke. With us, because the implementation is based on a lightweight framework, we literally implemented everything. So when something breaks, it's totally our fault. But that's part of the beauty of it. We can actually fix everything. And we're not as dependent on Apple or Google for anything other than the ability to draw, which is mostly consistent and doesn't break as often. And that provides us a huge level of portability. And there's a good reason that lightweight frameworks existed through history, and that's for portability. They were invented during the age of Smalltalk and later on advocated by people who needed extreme levels of portability. And that's a huge advantage, undisputed, of lightweight frameworks. On the other side, OS conventions are sometimes harder to get from lightweight frameworks. So native frameworks automatically get the OS conventions without a problem. We use theming to give OS style behavior, but obviously it's sometimes a race to keep up with the way an operating system behaves. So nuances might exist. That's always a trade-off between portability, ease of use that we provide, and customizability. And on the other hand, it's OS conventions. Now, the ability to be consistent is another advantage of lightweight frameworks, where we can customize the application to be pixel perfect to the way your designer envisioned it. And that's something that's much harder to do with a heavyweight framework, because sometimes one operating system will behave in one way and another, even from the same vendor. So an Android version X from Samsung might behave differently from Android version Y from HTC. And it's really hard to get these things to match up perfectly with a heavyweight framework, but we can get pixel perfect behavior. And one of the nice things here is performance. So a lot of times performance is very portable. So when you look at a specific use case where performance isn't as great, the solution to performance is, in at least 90% of the cases, is to cache data, keep it in memory, or keep it in the GPU and the graphic processing unit. And to do that, we need to load the right data in advance, put it in the right place, and make sure it works fast enough. And when we do an optimization like that, it's usually very portable. And because most of the code is written in Java in our case, and its performance will be very consistent across platforms. So if we optimize something in caching or in some other strategy for Android, this optimization will work similarly to iOS, etc. So this is a huge advantage of lightweight solutions. With heavyweight solutions, performance is sometimes good because heavyweight widgets themselves are optimized by the operating system, but their behavior isn't consistent. So something that might make a heavyweight widget like a list behave quickly on iOS might make it behave more slowly on Android. And so you end up with a lot of nuance when it comes to performance that's really hard to get right across operating systems. And some of the strategies might not translate as well from iOS to Android and so forth. So this is a very debatable and complex issue, the issue of performance. The heavyweight frameworks are easier to build for the framework designer. So it's if someone wants to build a framework, it's much easier to build a heavyweight one than lightweight one. That's what I meant by the easier to build. It was probably what I was thinking. And the last bit about heavyweight, and by the way, I really struggled trying to find entries that would make heavyweight seem good, to find the advantages column, because honestly that's a bit of confirmation bias, but there isn't that much other than matches OS conventions and potentially performant. So access to native OS features, essentially when you want to do to include a feature like Google Maps, for instance. So in Codename One, you can add Google Maps, but that's because we added a peer component. And that's a bit challenging. You need to know how to do that, and you need to add a peer, and it's not as bad today. It actually works relatively well today to do that. But it's not as easy as some of the native frameworks allow you to. Of the heavyweight frameworks that allow you to do that. And in that sense, it's a bit harder sometimes. So it's possible in both, but in Codename One, because of the lightweight architecture, we draw things, and then if you add something like a map, which is drawn by the system, we need to know when to draw on top of it and when to draw below it. And that is sometimes a bit complex, and we also lay it out. So there's various nuances that you need to be familiar with when it comes to dealing with peer components. And with a heavyweight framework, it works a bit better. So in Codename One, as I mentioned earlier, native peers are supported, which is really important. Some of the lightweight frameworks don't allow it. So for instance, Qt doesn't allow it. Swing has issues with it. Actually not that far from our issues that we had with it. But it's a pretty big deal, because usually lightweight frameworks don't support native peers, and we think that's really important that we do. We also support Z ordering in native components, which is also very important, being able to put something on top of that. Now, the simulator, which is a point that I didn't mention earlier, is enabled thanks to the lightweight architecture. Because we draw everything, we can simulate everything on our own, and we don't need a Mac for that in order to debug. The moment that exists, we don't need a Mac at all. So we can use the cloud build to actually build the native application and go directly to device, because we can debug locally and then go directly to the device. We don't need that thing. And with native frameworks, that's not an option. So cloud build would be redundant because you'd need a Mac anyway. So with heavyweight widgets, it's redundant in that sense. Now, Codename One, as I said, is very performant because we use OpenGL to do all the drawing and everything, so it has native level of performance. Just like games are fast, Codename One is fast. And it was optimized during the days of feature phones. So if it ran on a 2 megabyte Nokia, it should run fine on a gigabyte worth of RAM on an iPhone. So it's a very efficient framework in that sense. And it's remarkably customizable. We control literally every pixel, and so do you. So you can literally change everything on the screen, and that's unparalleled by heavyweight widget solutions. So I hope this presentation gave you the tools to understand what's a part of Codename One, where it came from, how big it is in terms of the functionality, and understand the pieces that comprise of it, and also how they all compete with one another for better and for worse. Thank you.